Okay, so let's continue, and we start to look for the last details, because we got the core of the physics, which is entering in the process of computing the power spectrum, or the density fluctuation power spectrum up to second order. And we realized that there is mode coupling and all the things that we have seen, and I already anticipated that now we need to link. Well, there are a few details that we can still fix. They are not going to be explicit computations because they are way too long, because they are very, fine-tuning of the procedure. But I'm going to show you what are the key steps up to the last one. So let's say you're going to get the state-of-the-art construction for the power spectrum. And as well, we need to consider the fact that we are not observing the matter field, but the one of galaxies. The board before I mistook, I used M and G here, that's actually the way around. Okay? So once you have your true fluctuation field for the matter, you multiply a bias term to link it to the distribution of galaxies. So that's the process I already mentioned earlier. So we have the true density fluctuations, and what we actually are using are tracers. Tracers which are galaxies, and as I also mentioned earlier, galaxies of different colors are different tracers. They trace the matter field in a different way. Because I mentioned that the red galaxies are most likely found in dense environments, for example, within galaxy clusters. Therefore, you are going to find them more clustered with respect to the blue ones that are found, that populates in large amount also the field. Therefore, the fluctuation sort of shallower if you use those galaxies. So you see, the bias might depend on the color of the galaxies that you are using. Okay? So there are all these complications there. And here you are seeing the simplest expression that we can possibly have, which was, let's say, the first formulation of the bias. But I'm going to show you that actually we are going to need further terms. Okay? We need to include other physics that we cannot neglect. Otherwise, we would misunderstood and misinterpret the observations. So let me make it bigger. No, airplane mode, like that. Good. And that's the state-of-the-art bias. This equation here. Okay? So people started and say, okay, so a linear bias is not what could be a constant. Okay, why not? The density field of the density could be follow exactly the same fluctuations, but there could be a constant factor. Okay, so the fluctuation would not be around zero at first order, but it could be boosted high for some reason. We don't know. It's not the case. Therefore, people say, okay, we don't need it. That's the bias I mentioned earlier, so that's fine at first order. But if we go at higher orders, we need to include also higher order terms. Yeah?
Does that come from observation that we cross out the constant?
Yes, observations and also physical considerations from simulations. Okay, so one it is a sort of an educated physical guess of how things are going. Okay, how to let's say use the minimum number of terms that is possible given things that you can observe.
And what is the physical reason behind the educated guess to cross out the constant?
Well, the reason is just that you have a density field at a linear order is center of zero reconstruction. Okay, that's how we define density minus the background divided the background. Okay, therefore, at first order, the fluctuations are centered on zero. And you expect that if you have an overdense region, you would have expect a number of galaxies, which is here. In an underdense region, you would expect less galaxies here. Okay, and at first order, the fluctuations are still centered around zero. You don't have a plateau, what to say. Okay. Okay, good. Then we have our linear term, and as I said, we could expand it to second order. Okay, so you see that from here to here is just a Taylor expansion of a function that depends only on delta. Then all those terms contains further physical contributions. Because, for example, we might have terms, you see these G2 terms, that depends on gradients of the gravitational potential. That's physics. Okay? This would mean that if this term is different than 0, we might have regions that might create more galaxies given a certain gravitational potential. Okay, gradients of gravitational potential, because it's flat, it doesn't make anything, right? So these gradients of gravitational potential might influence the formation of structures, and they do. For example, through merging. Okay? We have a larger cluster, this guy, or a larger object, or larger galaxy, this galaxy can swallow other galaxies. And therefore, if we count galaxies, the number of galaxies in the surrounding of big ones is depleted, because everything is swallowed. And therefore, we would expect a contribution given by the gravity. Therefore, the observed fluctuation field do not depend only on the one of matter, but the one of potential, of the potential. And we might even have a contribution associated to velocity field, for example. Okay? And this is a construction that has been inspired, if you want, by observations as well as numerical simulations. Okay? And again, I split it in a Taylor expansion, a simple Taylor expansion where only delta is used, and these other terms where they contribute, where you have the contribution of physically motivated terms. Okay? You find all details in this paper here. Nice. Then people say, okay, that's the most general thing that we can use, but it's overcomplicated, and actually we can neglect this term. So we can say, let's forget about those, they are irrelevant. Why they're irrelevant? Because they are redundant. Okay, they are actually not free, new degrees of freedom, but they are correlated to other quantities. And therefore, they can be neglected. Okay, they are just redundant terms. And we are left with 4 biased terms. So these are the 4 additional parameters that we need to fit at the cosmological, in our cosmological analysis. We don't only have the cosmological parameters such as omega m, omega lambda, and blah blah blah, all of that, the equation of state of dark energy, if we are using dark energy, but we have these additional terms that relates the cosmological theoretical prediction to something which is observable. And therefore, these terms swallow, if you want, all the terms related to astrophysics. Okay, to astrophysical process, galaxy formation. Nice. And therefore, the power spectrum is going to be the one that we have seen before, but with respect to galaxies. Okay, so the real power spectrum that you observe is actually this one. It's not delta m, delta m. It's the density contrast of galaxies and density contrast of galaxies, in which you have these additional terms. Therefore, what you do, you use this expression within that. And you go through the machinery that I showed you earlier, where of course we are going to have the terms that we have seen earlier, this delta m, with a constant factor in front. That's what we derived earlier, except that there is this constant factor in front. Then we have all the terms and the multiplication one with each other. Derivations are very long, I spare you that because it doesn't bring you any understanding, but you realize that you arrive at a final power spectrum that includes observational quantities. Before showing you the final result, we need to realize another thing. That, damn it, we are observing galaxies and they move. They have a proper motion. And therefore, the redshift that we observe is not the cosmological redshift, right? Because whenever you are computing your delta m, that's as a function of redshift. But that's the cosmological redshift. Galaxies do have a proper motion. And therefore, there is a redshift contribution coming from the motion along the line of sight. That you can see. we have the observer, we have a galaxy here, which is moving with the bulk flow of the expansion. That's our cosmological term. But there is the contribution along the line of sight of its proper motion. So what we do? We get the velocity of the galaxies, which is statistically predicted by our velocity perturbation field. That's what is tracing. And we can project the velocity on the component, just use the component along the line of sight, which is zero. Therefore, from the purely Hubble expansion term, now I set c equal to 1 so that it's easier to trace velocities with redshift terms. So we have our velocity expansion and we have a contribution which is given by the projection of the velocity along the line of sight. That's this guy. But damn it, not enough, we are moving as well. Because we are moving around the Sun. The Sun is revolving around the galaxy. The galaxy is moving within the local group, and so on and so forth. Therefore, there is a local velocity component that we need to subtract. Okay? Therefore, we have this velocity, which is actually the one that we observe if we associate it to a Doppler shift. Cosmological contribution, proper motion of the galaxy, velocity of the observer as on the Earth. Okay? Then we have a linear theory. We have linear theory for which we have a direct link between the velocity and the density contrast. That's what we've seen in previous lectures. Okay? But if you have a density contrast, that's just, or the velocity is just along the k mode. Okay? Along a mode. Nice. So that's the point, the proportionality between V and delta. Therefore, what you do, you consider this equation now for the observations. You have a direct link because V is going to be this guy in the Fourier space, and then you can correct for the density contrast. And what you obtain is this equation. So you have the true one, if we wanted to call it so, the one associated to the cosmological redshift, times 1, this will be what we considered earlier, plus a contribution which depends on the angle of where we are observing, and this factor beta, which is called redshift distortion parameter. Okay? Redshift distortion parameter is nothing but that's coming from this equation there that links to theory, is just the ratio between the growth factor and the bias at first order. Okay, that's defined like this, and that in the link is coming from here. Okay, so we have this correction. Therefore, the first part, the power spectrum. Now, I just write the linear regime for simplicity, otherwise we get something ugly. You see that your bias for observed galaxies, the linear term, considering the velocity distortion, contains this beta, so that's the linear contribution of the bias, and then you have the redshift distortion contribution, okay, due to the proper motion of galaxies and of ourselves across the universe. If we want to look the picture, the full picture, if we go to second order, that's the ugly equation I was mentioning. Okay? So we have the galaxy power spectrum, including the redshift space distortion, so that's this redshift correction that I mentioned, where we have this correction function, which is Z1, Z2, and so on and so forth, in Z3 down there. Okay? Where Z2 is not just a cute little expression, but it is an ugly guy here. So you see, things get quite complicated very easily. Where we have the bias term that enters as a multiplicative factor to the kernel that has the original shape that enters in the power spectrum, okay, plus a redshift distortion contribution that is multiplied to the original velocity dispersion kernel. And here you see that the velocity term is the one that is correcting or is accounted for the velocity, the proper motion of galaxies. Okay, so the velocity field kernel enters here, together with weighted with respect to the growth factor bias that we have seen before. And then we have a second order term bias that is appearing here, and then that is just an extra kernel like S1, which is just this term here. Okay, and mu is just defined as the ratio between the K mode normalized with respect to redshift. Okay, just numerical terms that are kept together. Just important to notice that there is an extra kernel. There are not only the original kernels before. Okay, we are not yet done. Now we are considering the fluctuations, but we are not happy enough, because if we go back to the plot that I showed you earlier, there is things improved a lot, because from these red points that is final, is our truth, our computations start to depart from reality already at this point. Why? Is it because we stopped the second order? No, that's not a matter of the expansion that we did earlier. The departure that is coming up here is because of the assumptions that we used. And the assumption that we used was that we neglected all rotational modes. So we only consider irrotational modes, which means that we have a structure which is forming, and this velocity is the relevant one, not this one. You have a large structure, you don't expect it to have a very relevant velocity in this sense, okay? It's collapsing if it's forming, okay? So it's moving in this direction. But when you start to enter in the linear regime, you understand that momentum conservation is kept, like the ballerina, we start to spin faster and faster. And therefore, these terms become relevant, okay? And the relevance of this term occurs before the relevance of higher order terms. So this is more important. This physical assumption is more important than the mathematical approximation that we used. They are called counter terms. Don't ask me why they are called like that, I don't know. But the ones that are related to this sort of motions are called counter terms. When we include the guys, that's what we get. The green curve. Look, nice, 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 nice. Let's say up to here. Then things get crazy again. But we are right here. So from here, say a K mode of 0.08 or 0.09, if you wish to push, we can describe the fluctuation of the power spectrum with a very good accuracy up to 0.1890 in terms of K numbers. Okay, up to here. Then we are split again. Okay, nice. Is it the end of the story? No. No, it's not the end of the story, because there is something else that we can do to do things better, and is to include the so-called infrared summation. Okay? What's that? This arises from the fact that there is an additional contribution to the power spectrum that is coming from the coupling of very large modes. That's the infrared regime, right? Low K, for that's in the infrared regime. That's just a terminology which is used for low Ks. To small scales. Okay? We had the kernel that were coupling the modes, but they were not complete, because we are using approximations and we are working at the second order, which were not accounting for very large modes, the coupling between very large modes and smaller modes, so higher Ks. Okay? Low Ks to high Ks. Therefore, what people do is to apply a correction not to the entire spectrum, but only to the wiggle terms. Okay? Because they are not going to change the slope or the power spectrum of anything of that, but they are just going to smooth a little bit the wiggles. Okay? If we have wiggles that have a certain width, no? There are fluctuations like this that we have seen before, like these guys here, okay, like this, they get a little bit smoothed down. So the height is a little bit lower and the borders a little bit fatter. Okay? That's what the infrared correction is doing, and is a very, very small correction. Like that. Okay? You see? You get a smoothing term when this is included. And the power spectrum looks like that. Okay? And again, this is a correction which is only applied to the wiggly part. So what you do is to split the power spectrum into terms, a no-wiggle one and a wiggle one, and apply this sort of convolution. Okay, that is coming from the large modes. Use a convolution that smooths the amplitude of the peaks, and then you put it back together with all other terms. What's going to happen in the final power spectrum is not that your peaks. Again, I'm going to show the power spectrum normalized with respect to the non-wiggle one. Okay, to the linear non-wiggle one. So you have like one, and then there are your wiggles. Okay. You're not going to have something like that. Okay, God, I mean, I'm not good at drawing this, but something like that. But you're going to have a shift, which goes in this direction. Why? Because you're actually doing that. That's the power spectrum. Okay, it goes something like that, and you are summing up a contribution here. Okay, and your contribution here is going to be like that. That's because you're not you're making a convolution of the non-wiggly mode, but when you sum it to the total power spectrum, you get a shift, because the derivative of you have not the derivative of the function describing the wiggles, but you have the derivative of the functions of the wiggle plus another function. And if you want to find the peak, derivative equal to 0, and you get a shift. Okay? So you're going to get a smoothing of the wiggles and a shift. It's small, but is there. And your final power spectrum is that one there. Is this one. Okay? That's your final power spectrum. But for the process, the final process is the following. You first compute the linear power spectrum, that you need it in any case, even if you want to go at higher order. You do all the derivation at second order. For the power spectrum, you realize the fact that you need to go at third order, because the correction at second order in the power spectrum, remember you have an average of the product of two quantities. And you have the product of quantities up to second order, and therefore it's fourth order for the power spectrum. But in the combination, when we did the symmetry before for the power spectrum, we have more the linear one times the second order. Okay? Sorry, we had if we would have gone to an higher order, we would have the first order times 3 order term, and that's again fourth order. Okay, so for the power spectrum, you need to include all terms up to fourth order in the power spectrum, which means you have to go up to third order for the density fluctuations. That's not the end of the story, because then you realize the fact that we are actually observing galaxies, and therefore we need to compute a bias term. And in the nonlinear regime, a linear term correction is not sufficient. Therefore, you need to include also nonlinear terms in your bias that account also for physics, for the astrophysics that goes from cosmic structure formation in terms of the dark matter distribution to the actual formation of galaxies. where you have star formation, run pressure stripping, and I don't know what is going into the machinery of the universe. Okay? Feedback and so on. So it's a complex machine which is captured by these higher order terms in the bias. Okay? Not enough, because galaxies are moving because of the proper motion, and we need to account for this correction through the velocity power spectrum. You know, we have the statistics for the velocity perturbations, we have computed them, and we need to account for them. And therefore there is a correction term. Not enough, because we made an approximation, and the approximation now was not mathematical because we did an expansion of a perturbation series, but it was a physical approximation. We initially assumed irrotational modes only. But when the structures start to become more and more nonlinear, then the rotational component gets more and more relevant because of angular momentum conservation reasons. Okay? Therefore, if we include them, the improvement in the power spectrum, without going to higher order, gets much better. Okay? It's sensible. And then there was a tiny correction that also people is using in the common cosmological analysis, is the one to include the infrared corrections that account for the fact that very large modes are coupled with smaller ones. And this coupling tends to smooth a little bit the amplitude of the wiggles, they make them a little bit flatter, and when you measure them in the total power spectrum, they result in a little shift. Okay? Good. So that's all about these lectures and what I wanted to discuss up to now. Okay? During cosmology, the semester, we have also seen that there are other techniques to go in the nonlinear regime. For example, there is the Z-Dulwich approximation, which is based on tracking the particles in the phase space instead of real space, and numerical simulations that we also discussed during the last lecture. These are, let's say, the key ingredients to describe cosmic structure formation in the nonlinear regime. And then there is also the spherical collapse. That's the other technique that we've seen during cosmology, in which we are assuming an object which is collapsing through and then we link it through by using the Friedman equations. We basically exploit the Friedman equations to describe a spherical region of a universe, an overdense region of the universe, as a universe on itself. Okay? So self-gravitating system, gravity, general relativity describes a self-gravitating system, and we use it to describe the evolution of the spherical collapse. And then we link it to the linear theory to know how many collapsed objects we have as a function of time and as a function of mass. That's the mass function that we've seen during your talk. Okay? These are let's say the spectrum of possibility of. And well, there is another one, which is, if you want, new, which is kinetic field theory. Okay? So kinetic field theory is another approach to describe the power spectrum at a higher order, and again exploit the phase-space distribution of particles. Okay? At the moment, a lot of progress is done in this field. It's promising, but is not yet ready for field tests, in the sense that the derivations that have been done are getting better, but are not accurate enough numerically to then make predictions for observable quantities, such as correlation function and point correlation, like or 3-point 2 and 3-point correlation function is done with these other techniques. Okay, good. I think that's a kind of close cosmic structure formation. Good. So I think that's the last lecture. We are going to have the last seminar during the afternoon. And since there is only one seminar, I will just speak a little bit about methodologies to approach cosmology. I will do it in a very informal way. And I'm not going to give you specifics about the techniques that are used, but I would like to give you the concepts, the power, and the limits of it. Okay? Because many times you can see that it's kind of abused. Because, yeah, I can do everything and anything, but then, yeah, careful. Okay? Because, the data are complex thing, and when you use a million parameter model, you know that things can go highly nonlinear. Okay, so one have to be extremely conscious and careful in doing that. So it's going to be a message more than a technical description of the topic itself. Okay, so a little bit of machine learning as well. Good. So I officially close the lectures now, and thank you very much for the attention. It was a pleasure, and I see you around later. Yeah, 2:30, it's fine. Just leave the display.
Because, like, okay, this is Gaussian, but this is non-Gaussian. And it's not clear to me why the combination of them, even though they're hot, they vanish.
So, I think that in the script of Luca there is no derivation. But the thing is that the fact that you tend to have so I think you're looking at this, so you should look at that. Okay, so physically you can think like that. If you would have a 2 or a 4, this is it turns out to be an even number. Okay, so it's like a power of 2 or power of 4, and therefore the average is positive. Whereas if you have that, since if you have 3 terms, then the contribution is going to give you both positive and negative numbers, and on average they vanish. And the Gaussianity is necessary because then you have the same amount of positive and negative contributions.
So order of 2 are like implicitly like powers.
Exactly, power of 2, power of 4, etc. etc. Okay. Basically, they give you positive terms, and they add up in the integral. They cannot cancel each other. If you have non-Gaussianities, then this is not valid anymore.
Yeah.
Okay, they fixed the script. I realized before the lecture that I was missing delta functions, including delta functions.
And also about the rotation, about the peculiar motion of galaxies, is that we have to take account of that, and also the motion of the observers.
Yes.
But why can't we just use stress frame? Because there are a lot of motions in the observer around the sun, around galaxies. Yes. Why don't we just use the rest frame of the observer?
Well, that's what we do. When we subtract our own velocity, that means going to a rest frame. I mean, or you transfer all observation in the rest frame of the observer, or you put yourself in the rest frame. That's what people does is simpler. For example, in the CMB, if you look at the CMB fluctuations that are coming from data, are dominated by the dipole contribution, which is our own motion. Okay? So what people do is that's our motion in the data, we remove it.
And then one more question about the last part, the IR resummation part.
Yes.
Is that we have to take into account the coupling between large and small
Yes.
nodes, but have we already done that?
Not completely. One part is missed.
Okay, which part is that?
I mean, the derivation, there are assumptions involved, and we stop the second order and not everything is captured. So there is still a bit of, it's more, but I don't even know if they managed to measure it, frankly. But if they compare with numerical simulations, they see that they include these terms better. Because there is this part of coupling which was not accounted for.
Right. So I thought in the second order we saw like we have integral over like decay, like dk1, dk2. So I thought we already include from the lower to the highest.
You integrate over the entire spectrum, and then you have to think that if you would have included higher order terms, you would have additional kernels popping up. Okay, and these are these additional terms of the coupling, and you're not going to think of those.
Okay, so like the third order that we missed.
The third, we use it for the power spectrum, because it's needed. But then there are still, fourth, fifth, and so on, there is still something. So it's used as a correction. So not going from the beginning with higher order, but you stop can do analytical stuff, and then you add it as a correction, and only on the wiggles, because it's easier to work there than. And also that one is not coming from first principle. It's not that for mathematics give you those terms. These are physically motivated functions. That are inspired by looking at the simulations and at the data, and then fit them. So they're not free parameters. It's not
It doesn't come from assumption.
It's not. They're really like the corrections plug by hand with should be like this and like that because gravity and blah 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 and all of that, and then you fit the parameters to the data to the simulations.
Like the one having the mass functions.
Sort of, yes, sort of. Yes.
Okay. Thank you.
Very good.